Alright, so here's the situation. We are climbing this thing, alright? Brett, we close that window back there. And we're right here at this point. Okay, standing at the bottom of this thing. And it's like this little canyon-y area. And then this looks just like Independence Monument. But it's a lot closer to the canyon wall. Independence Monument, you know, it's kind of far out there in the middle by itself. This one's a little bit closer to the cliff. So we climbed this next. And I'll show you some pictures of that. So what happens when you do multi-pitch routes, which means the route is longer than the rope you have. One person climbs to a point like this and then gets anchored into the wall, and then the other person will climb up next. So I'm climbing up this route right here and cleaning the route, which means I have to take out all of these little pieces right here, and those are what we're actually relying on to, if we fall, to save our lives. So what they are, they're called a cam. And a cam is like if you had your hand and you jammed it into the crack in the rock and then you made a fist, wouldn't it be hard to kind of pull it back out? That's how a cam works, except it's a piece of metal. It's got like a little trigger and you squeeze it and it gets really small. And then you put the cam in the crack here and then you release the trigger and it expands in there. It's like a claw and it won't come back out. So then you take a little piece of webbing and a carabiner and you clip the rope right into there. Does that make sense? So you don't want to leave those things because they're like $70 each. So you don't leave them in the rock. So my friend Tom is up here. He's already climbed the route and I'm taking all of these out. It's called cleaning the route. So then, still coming up the route here, and then we switch. So then he needs to rest, so I'm going to climb first. Alright, so now I'm putting these cams into the rock here. And so if I fell from right here, where would I go down to? I would fall down past this, all the way down to here. It's kind of scary, yes. So you don't like to climb very high above your last cam, if that makes sense. So what I'm probably trying to do right here is place another one, so if I did fall, I wouldn't go anywhere. Alright, but maybe like a foot of rope stretch. And this, for me, was probably the scariest part. Okay, so right there, I'm probably trying to fix one. Okay, and then I put a cam right there, you see that? So now if I fell, I would actually not fall very far vertically, but I would swing all the way over here. Alright, what's the tension in the rope right here? Zero, it's slack, okay? So my climbing partner's feeding me feet of rope here as we're going, alright, but it's slack. It's not going to have a tension until you put your weight on it. Okay, then we got to the top, and so we're both standing up here. And I didn't really know what was going to happen next. My friend Tom does this all the time. He's like, hey, just come along. It'll be fun. I'm like, okay, whatever. So we get to the top, and I'm thinking we're going to rappel off this side and hike out. But we didn't. We went from here over to there. No, we did not base jump off of it. That would be I wish we did. That'd be a cool skill. Okay, now how the heck would we do that?
Do you have flight suits?
We did not fly, use rocket packs, we used ropes.
Through a rope with a grappling hook.
Through a rope with a well, kind of, not quite. Okay, so here's me hanging in between these two cliffs. So, that's me right there.
That's kind of cool.
Okay, and the rope's going down to me and back to that side. And it was really, really scary. It's called a Tyrolean. So what happened was when we were climbing this part right here, we actually had a rope. We had two ropes. So we had one that, I think we tied it to our backs maybe. I can't remember how we did it, but it just went like this. And as we climbed, you guys see what I'm saying?
Yeah.
So as we climbed, it just sort of followed us up, but it was always fixed over here somewhere. Okay, so then we were able to set up this line. We pulled it to a certain amount of tension, and then we went across. So when I was hanging right here in the middle of this whole thing, and there's like snow, it was crazy. I heard my phone ring, but my phone was on this side in a backpack, and he answered it. He answered my phone while I'm hanging in the middle of this thing. While he's supposed to be like watching for my safety and whatnot, he answers my phone. He's talking about it. He's like, oh yeah, he's fine. He's hanging in the middle of a chasm. He's talking to my wife, who was probably like, you're not hanging out with this dude anymore. So to get across, you have this, you're tied into this with your harness, with your climbing harness, and you have a piece of equipment called a Jumar. And it's a metal device that when you slide it along the rope, it will slide this direction, but it won't go the other way. So you slide it and it locks out, slide it and it locks out. So that's how you get back up this.
You just pull yourself up the rope?
Yeah, you kind of pull like that, and then you slide the Jumar up and down the rope. Well, just up.
I have a question.
Yeah?
So when Tom went to the other side, how did you take his rope with him?
You'll see. Okay, so I've got this second rope here, which is the safety rope, but to me it's not much of a safety rope because if the main rope breaks, all I'm going to do is pendulum to the other side. So if I'm right here and it breaks, I'm just going to go bam. So I was like, wow, what a safety rope. Okay, so you can see I'm almost to the side now. He's going to go across, and check this out. He's got 2 ropes, double-stranded right here, and he sent me first, so I realized that first hour. So I'm calling him after school and asking him why I had to go first here. All right, but now what's happened is the 2 ropes have been tied together, and they're both fixed on the other side, and so he's coming across on those 2 ropes, and then once we're done, we just pull them through there's like eye bolts up here, and you just simply pull them through, and you don't even have to leave anything on the other side. As long as somebody's fixed some metal eye bolts in here, it's fine. So now he's going to come across this thing, and you can see how far down it is. It's pretty deep. That's pretty vertical right there. So those trees look pretty small. Alright, and let's look at this picture right here. And we'll actually call this Climber 3 and analyze the forces here. Okay, so we're going to assume the person is right in the middle. So let's draw their center of mass. And the blue lines are going to represent the ropes. So we got a rope coming out like that. We got a rope kind of coming out like that. It's supposed to be straight lines. Alright, and then here we're going to make this dotted line the horizontal. If the climber is directly in the middle, then our angles are the same. So I actually estimated the angle to be 20 degrees with the horizontal. Just from looking at the picture. Okay, and sticking a protractor on there, it's about 20 degrees. Alright, now I haven't drawn any forces yet. Okay, the blue lines do not represent forces, they're just a picture. Okay, what force can we draw super easily? We can draw mg. Okay, so we got the climber's weight, and we already know that is 668 newtons. from the previous two problems. And then we got a couple of tension forces. So tension can only act along the rope. So I'm going to call this over here T1. And then we've got another force of tension over here. We'll call that T2. Alright, so to hold up weight, we have to have a vertical force, okay? Is tension vertical?
No.
No, it's off at an angle. Okay, so what is holding up the climber's weight here?
The vertical components.
Okay, so we need to break this down into a triangle a little bit. Use dotted lines. We're going to call this TY1. And then over here we'll call this TY2. Just means tension in the Y direction, and the 1 and the 2 tells you the side.
Don't they equal the same thing?
Alright, and then we also have horizontal components, so let's put those into. So here we have tension in the X direction, 2. Tension in the X direction, 1. And now we're beginning to see some vertical forces that can hold this person up. So these two right here together are supporting the 668. So up here, let's say that Ty2 plus Ty1 equals 668. Or we could just say mg. Okay, now, since this is a special case, the person is right in the middle, these angles are the same, that means these are the same too. Okay? So I can go over here and just say, alright, well, if they're the same, that means that I've got 334 newtons being held up by this one, and same with this side. Alright, now, what are the X components doing? Any ideas? First of all, the X components are the same. This X equals that X there. They are canceling. Okay, what are they doing in the real world for the person? Yep, Brock?
Well, I almost had an idea.
Okay.
It was like,
It lost.
Okay. Alright. Carl, what do you think? Any ideas?
No, I must have lost it.
Okay, Blake?
Are they keeping the rope at that angle?
Yes, you could say they're keeping the rope at that angle. Okay, Devin?
is it keeping the tension onto the rock on each side?
Yes, it's doing that too. But the Y components are as well. Okay, JT?
Keeping the climber still.
Yeah, they're just keeping him still. They're keeping him from moving in this direction. They're keeping him from swinging. And they're keeping him from sliding along the rope. Okay? So basically they're stabilizing the person. Alright? If that weren't true, the climber would either swing or start moving along the rope. Okay? Alright, now, let's say we want less, well, wait, we gotta do one important thing first. I almost forgot. We gotta find the tension in the rope, because that would be something we'd care about. Rope tensions are important because ropes have breaking strengths. So let's see if this is a reasonable tension. We've got a side and an angle. Okay, do it real quick. Find tension. Solve for the hypotenuse. Alright, so SOHCAHTOA. Opposite side's that. Hypotenuse is that, T1. So if we want T1, we gotta say T1 equals Ty1 over sine theta. Or 334 divided by sine 20. Okay, Tony, what do we get there? 976.5. You guys agree?
Yeah.
Okay, alright. We could round it or whatever. Alright, now that is a tension greater than the climber's weight. Okay? So, in this configuration, we actually have to have more tension than the mg to support the climber. Okay? Now, let's say we wanted less tension in the rope. What would we do?
Loosen it.
Okay? Increase the angle or decrease the angle is the question. Okay, I heard both answers. Let's try it out. Okay, do 334 over sine of 10. Let's cut the angle in half. All right, Aubrey, what do we get for that one?
1,923.
1,923. Okay, more than doubles, right? Okay, so we tighten the rope, right, by pulling some slack out on the other side, and our tension doubled even more. Okay, let's go down, let's really tighten the rope up. What about sine of 1?
What's it like?
Okay, what do we get there? Sine of 1. Okay, right?
19,137.
Okay, so let's round that to 20,000. 20,000 newtons if we have a 1 degree angle. 1 degree is basically flat, right? Okay, let's take 20,000 and divide it by the climber's weight real quick. See how many times greater it is. All right, Jessica, what do we get? 29 point something? Yeah? Okay, so that's almost 30 times the climber's weight. So it would be like hanging the rope vertically and putting 30, well, there's 30 people in here. So if all 30 of us got on the rope and clung to it, and we're all hanging here, right? Okay, here's 30 people hanging from this rope. Do you think the rope's made for that? Probably not. Okay? Now, maybe 30 of us just hanging there, it might be able to support us, but let's say 30 of us were falling and the rope had to catch us and stop us. Now can it support us? No way. Okay, that's going to be more force than just hanging from it. Alright?
So I did 334 divided by the sine of 30, and it was exactly 668. So what would that mean in the context of the problem?
Okay, so at a 30 degree angle, this tension was 668. That's what you're saying? Okay, now the y component is still 334. No matter what angle we use, the y component has to be 334. So you found the place where, yeah, the tension equals the mg of the climber.
Alright.
Yeah, it's the same as if the climber was hanging straight down. And the difference is we got 2 ropes now. Okay, now do we really have 2 ropes in this situation? Not really. Okay, we actually have 1 rope that's kind of fixed at a point, so it sort of acts like 2 ropes or 2 cables. All right, now let's just for fun try a sine of 0.1 degrees. Say we get it really, really tight. Okay, Brittany, what do we get for that? 191,000 newtons. Okay, so as theta approaches 0, tension approaches infinity. Yeah.
Limits.
That sounds like some calculus, like some limits, right? Okay. All right. So, we do not want the rope super tight. The tighter we get that rope across there, the more likely it is to break. That's what we're saying here. Okay? If we decrease that angle so the person's hanging way, way down in there, that's not convenient, so we gotta find the happy medium for the situation, okay? And make it work out, alright, questions? Yeah.
Yeah, so if they were to ask a problem like this on the AP exam, would you have to prove that those two triangles are congruent?
Well, if they gave you the angle 20 and 20, then you wouldn't have to go into that much detail. Okay, Carl?
Because like it's one solid rope, I mean, isn't that force being put on that one point in between?
The tension is actually the same throughout the entire rope. Yeah. And you'll learn that the more we talk about this, you'll realize that the tension is actually the same everywhere, not just at this little point. Okay, that's a good point. KT?
Is it possible to have like two Y components equal more than the weight, like,
Well, if the person's going to accelerate upwards,
oh, so like
it's like a bungee jump or something. Once it starts going in that direction, the tension is greater than the bungee jumper's weight. And yeah, it's gonna shoot him upward. Okay, Nick?
Can that rope handle that much tension?
Yeah, now this right here is totally reasonable. 976, that is no big deal for a
Like-
climbing rope.
191,000 tension?
No, 191,000. We could look up the breaking strength of different ropes, and we've actually done that before. I don't really have a number in my head right now. But yeah, there's a rating for all this stuff. Okay, so let's see if I have any other pictures. Here's a close-up. There's a lot of carabiners and stuff in here that have to make this system work.
I like this Tom guy.
Yeah, he's crazy. Okay, there's Independence Monument in the background. So it's just right next door. They're kind of next door neighbors. So when you guys are driving around, you can check this place out. It's pretty cool. Here's the same thing in Yosemite. All right, this is not us anymore. Okay, but I like this one because check this out. If we highlight the rope in black here and we put the weight on there, now we've got tensions that are not the same because our angles are different. So I've got a shallow angle right here, and then I got a bigger angle right there. Now what happens here is if you work out the vectors, this one is a smaller angle. We just said smaller angle, more tension, right? Okay, but if we have this situation, this one will actually have less. Okay, and it's because the y component on this vector is bigger and it's holding up more of the climber's weight. Before, both sides were equal. Okay, now here, it's holding up less of the weight because the y component is less. Now what is the same for these two triangles though?
Horizontal.
The x is still the same. Alright? We'll do this problem later where we have differing angles. It's a little bit more tricky. Okay, other situations where you might see this, a clothesline. Not quite as exciting, but very practical, right? If you stretch a clothesline super tight and hang just a small amount of wet clothes from it, it could break. Alright? Because you are maxing it out because your angle is too small. Zip line. Anybody ever done this? Okay, they have one in Glenwood Canyon. I got to do this in Costa Rica, and it was like a rainforest canopy, and you could fly kind of through the trees and stuff. And then they had one really long one that went across a canyon at the end. All right, super fun. But look at the angle here. Not very big angles, because what are we using now? We're using metal. We're using cables. We're using steel. Okay. Yeah, I was meaning materials and stuff. Okay. A high line is a system like this that they use to transport supplies back and forth for construction and things like that. All right, they got to keep in mind all that tension rating stuff. A slack line, very doable in your backyard. And really good training for any athletic activity because it teaches you what? Balance. And you need balance whether you play tennis, skiing, rock climbing, whatever. Okay? Football, all of that. You need balance. You need a strong core. all right? And this kind of teaches that. So basically you stretch a tightrope and you walk back and forth and you can, you know, do different tricks. I've seen people like jump and turn around and do things, and it's kind of a fun park activity. Anybody set one of these up before? Yeah, it's kind of fun. Try it on your next break, Thanksgiving. It's really hard at first. Okay, so you guys don't think I'm making this up. Let's do this demonstration. Okay, what happens to these forces as I decrease my angle? Okay, you guys see those needles climbing? Alright, and here I've maxed out the scales. Okay? Alright, less tension if I do that. Okay. Alright, now we're going to switch gears a little bit. Last thing we're going to do today is the back of your notes. There's one example. One example problem with friction, and then we'll be done.
Which one?
Okay, so you turn to this side. Alright, and let's separate each of these parts like that. Alright, and here's the situation. This is a problem where we have to deal with both static and kinetic friction. We haven't really done that yet. Okay, so let's say we have a 10 kilogram box. Let's pretend that this system here is 10 kilograms. Alright, and it's just sitting there. We're going to only pull horizontally in this example. No pulling up at angles like we've done. Okay, just straight horizontally. And we've got two mu values. For static, it's 0.4, and kinetic, it's 0.3. Okay? So situations where we are breaking free of static friction like that, we actually get more friction than when we are moving. Okay? Static friction is greater than kinetic. Alright, why would that be? Okay. Inertia is a really good guess, okay? But the inertia is going to kind of determine more about how much force we have to use to start it rather than what friction's doing. Okay? Yeah, you got to overcome the static. Okay, so what happens is this wood, the molecules in the wood kind of lock together with the desk. Alright, they don't like chemically bond or anything like that. Okay, but they kind of lock together nicely, and then once you break that sort of connection and you're moving, then it's easier to pull it. Okay? So that's not a real detailed answer, but that's the general thing that's going on. We're not going to like look at it on an atomic level or anything. Alright, so with that said, we are going to apply these forces. So those are all force applied. So this is FA. And let's draw a couple FBDs. We won't do one for every piece here, but we will do a couple. So we got mg, and we got normal force, and there is zero force applied. Okay, so how much friction is happening here if there's zero force applied? Is there static friction here right now? We want to say friction is kind of holding it in place, but what we have to remember about static friction is that it is, I hear crickets. Lazy, yes. It is a lazy force. So if I don't mess with this, friction won't do anything. Okay? So they would like us to find friction for each of these situations. So force of friction is equal to 0. It's not going to act. It's lazy. It only works if it has to. Alright. Now, if I pull with 10 newtons, am I going to move it? We don't know without doing a calculation.
Are we holding or pushing?
It doesn't matter, pulling or pushing.
Yeah, you should.
Okay, so let's look at this. Let's draw this again. Okay, we got normal. We got mg. And let's draw this as our 10 newtons of force applied. Okay, we got the fun equation. And this equation right here will calculate static max. Okay, since static friction is a lazy force, it can act with all kinds of amounts of force. This, if you do this calculation, it is always only calculating the maximum. And we wrote that above in our notes there. Okay, so let's figure out what the maximum friction is. We've got 0.4 times a normal force equal to mg, which is 98 newtons. Okay, 0.4 times 98. We get 39.2. Alright. So, we're only using 10. Static max will max out at 39.2. Is it going to budge? No, we haven't overcome friction. So, force static is actually only going to go to 10. If it used the maximum, weird things would happen. That means if I pulled with 10 newtons, friction would say, oh no you don't, and pull back with 39.2 and pull it out of my hands. Okay, it's a good thing that friction's a lazy force. Static friction's a lazy force. Okay, or weird things like that would happen. Alright, so what if we pull with 20 newtons? What's static friction going to do? Fs equals 20 newtons. What if we pull with 38? Are we going to overcome friction? No. Force of static friction is 38 newtons. Okay, oh, now we are going to use 40 newtons of force. Okay, now are we going to budge this thing? Yeah, we're going to get it to budge, and we're going to overcome friction. Okay, so we are not using static anymore. What are we using? Kinetic friction. So let's draw this one. And we've got FA equal to 40. We've got FK, kinetic friction. We don't know what it is yet, so we'll just put a question mark. And we've still got mg and normal force canceling each other out. Like so. Okay, and all we have to do is use the fun equation. So Fk equals mu k normal. And we're simply going to change the mu to 0.3 this time. So 0.3 times 98. 29.4. Okay, so let's compare these two things. Friction went down drastically here. Okay? The kinetic friction is way less because of that 0.3. Last thing we'll do today. Let's draw a general graph for the whole situation down here. If you don't have room down there, you can put it up here in your notes. Okay, here I'm going to put force applied on this axis. Okay, Paige?
So, for part E, you just solved for the kinetic friction.
Yeah.
So is that just the general like you did for first one?
Yeah, it's just the general. Now with this number, here's the deal. It doesn't matter how much force I apply. Once this thing is moving, this is going to stay constant. Okay, and our graph will help us out with that here in a second. So this over here is force of friction. If I have 0 force applied, what's my friction? 0. So we're going to start at the origin. And then we said friction is just going to respond to our force. And the slope of this line is 1, by the way, because if I apply 1 Newton, friction applies 1 Newton. So we've got a slope of 1, and then at this 39.2, this is also 39.2. Here's where we're gonna break free. So the graph is gonna take a dramatic drop right here. And now, no matter what force I apply, the kinetic friction is just gonna stay at 29.5. So this line right here, going across, 29.5 newtons. Okay, so we got static, kinetic. Okay, any questions? How do you guys feel about that? Can't really argue with it. I mean, it's physics. We don't really have a choice. So maybe not how do you feel about it, but do you understand it?
Yes.
Okay. All right, Brian, you can stop that.